Hello, this is Ms. DB, and today we're going to talk about piecewise functions. Our objectives are to write and graph piecewise functions and to use piecewise functions to describe real-world situations. So, what is a piecewise function? It is a function that is a combination of one or more functions, usually more than one. The rule for a piecewise function is different for different parts or pieces of the domain. For instance, movie ticket prices are often different for different age groups. So the function for movie ticket prices would assign a different value, a ticket price, for each domain interval, age group. In fact, ticket prices for lots of different places are examples of piecewise functions. If there are different prices for different ages, then it's a piecewise function. It's not just ticket prices, though. We'll look at some other type of things that are piecewise functions. So if we use interval notation, square brackets indicate that you want to include that endpoint, and the curved parentheses mean not to include it. We went over that way back at the beginning of the year. But you can also use, if you don't want to, like let's say you want to say that the domain is greater than 0 and less than 5, and then your second part of the domain might be 5 and older, so then you would use less than or equal to. So this is that x is greater than or equal to 5. And this part is x is less than 5. Because if you have somebody who's 5, you need to know, is that going to be in the lower ticket price or in the next ticket price? All right, so we're going to use both tables, graphs, and verbal descriptions and equations written in function notation to work on these problems, just like we went over in 9.1. So here we have a graph that's given to us. And the question says, create a table and a verbal description to describe this graph, to represent this graph. So a table is just going to be, you're going to put the x values, which is the weight, and the y values, which is the price per pound, in your table. So note that there is an open circle here and a closed circle here. There will always be an open circle and a closed circle for the same number. You can't have both closed circles because then, like, the 5-year-old doesn't know which price to pay. Okay, so here's the graph again. It got a little bit chopped up, but we'll be able to figure it out. And for our table, those weights under 2 pounds were $8. So the price per pound is $8. So for your table, you could write 0 to 1.99, $1.99, if you had to say less than 2. This is to the nearest cent since it's price. And then we went from 2 pounds to less than 4. Oh, it must be less than 5. It got cut off, like I said. So that would be 2 to 4.99. That's weights 2 and under 5. And then for 5 or more, it's $5 a pound. So as many things, the more you buy, the less it costs. So the square bracket means to include that number. The curved bracket means don't include that number. Now, this is not the only way to write the domain in this interval notation. I could have written, and I may probably have written it this way, except x maybe we would call w or something. And then this would be less than 2, not less than or equal. And then for the second part, I would put 2 and then less than or equal to our variable, which would be less than 5, not equal to 5. And then for the last part, I would want to include the 5 in this third section. And that would be less than, I guess, infinity. So from 5 to infinity. Or we could just say that x is greater than or equal to 5, then it would fit this last category of 5 pounds or more. And then we have to write our verbal description, and that is just trying to explain what's going on so that other people could understand it. So mixed nuts cost $8 per pound for less than 2 pounds, $6 a pound for 2 pounds or more and less than 5 pounds, or you might say between 2 and 5 pounds, and $5 per pound for 5 or more pounds. A piecewise function that is constant for each interval of its domain, like we just looked at, such as ticket prices or the price per pound, that's called a step function because if you look at the graph, it really does look like steps. we can describe piecewise functions with a function rule. The rule for the movie ticket prices from example 1 on page 662 is shown here. So if the person going to the movie is less than 13, or as they wrote it, 0 is between 0 and 13, then it's $5. It's $9 between 13 and 45, including 55, sorry, and $6.5 if x is greater than or equal to 55. And that's the way I just wrote mine too. We read this as f of x, the function notation. You should know that. And then you can read the rest there. To evaluate any piecewise function for a specific input, find the interval of the domain that matches that input and then use that rule to figure it out. There's several of these on your worksheet. So here we have evaluate each piecewise function for x equals -1 and x equals 4. So for -1, we find the part that matches the domain over here. Where would the -1 fit? Is it less than or equal to 2, or is it greater than 2? It's this one. So we're going to use this part of the function to evaluate. But we're not done. Once we have the right part, we still have to plug the -1 in and find a value. So you'll get numbers for answers for these. So when h of x, when x is equal to -1, we go 2 times -1, that's -2. -2 plus 1 is equal to -1. So h of -1 is -1. For h of 4, that is x is greater than 2, so we would put it right here. So we'd go 4 squared minus 4. 4 squared is 16. 16 minus 4 is 12. So h of 4 is equal to 12. Sorry about that. All right, so in this example, we have g of x equals either 2 to the x if x is less than or equal to -1, or g of x equals 5x if x is greater than -1. So if we want to evaluate, this is at the same when x is -1, and what was the other one? X equals 4. So we're using the same values for x. So at -1, that is less than or equal to -1. -1 fits in this part because of the or equal to. So we use 2 to the x, but we have to replace x with -1, and 2 to the -1 is the same as 1/2. And then for 4, that's obviously greater than -1, so we'd use the 5x part, and 5 times 4 is 20. So they're pretty simple. You just have to make sure you pick the right part. Okay, now for this example, we want to use x equals -1 again and x equals 3. So this one, you can have piecewise functions in many different parts, and this one has 3 parts, and x equals -1, where would that fit? Is it less than -3? No. Is it between -3 and 6? Yes, it fits here. So that means that f of x is 15. So at f of -1, it's just plain old 15. We don't multiply it by anything, nothing. We just had to pick what it was equal to. Then for f of 4, that is also in between -3 and 6. So it's also going to be equal to 15. There was no math needed there because these were just constants, so we just had to pick the right constant to match the input. And in this example, we'll have to plug in the values once we find the right place to put them. -1 would fit with x is less than 0. So we're going to go 3 times -1 squared plus 1. Now remember that when you square a number, whether it's negative or positive, you're going to get a positive number. So this would be 3 times 1 plus 1. And 3 times 1 is 3. So 3 plus 1 is equal to 4. So that means that g of -1 is equal to 4. Our answer is 4. For 4, we'll plug that one into the second part because it's greater than or equal to 0. So we'd have 5 times, oh, it's not 4, sorry, it's 3. So we'd have 5 times 3, which is 15, minus 2, and that's 13. So that means that g of 3 is equal to 13. Here's some examples from your worksheet. You're going to use the values of x equals -8 and x equals 5 each time. So you find the matching part of the piecewise function, and then you evaluate by plugging it in and solving. So in number 5, for x equals negative 8, that fits with the first part. So we would go 2 times negative 8. I'm going to write f of negative 8 equals, and then you'd simplify that and you'd get that f of negative 8 is equal to negative 16. When x equals 5, then we'd have to use the second part because that means we need x is greater than or equal to 0. 5 is, so f of 5 is just 0. There's nothing to multiply, it's just a constant. Let's look at number 8. In number 8, we have k of x equals 15 if x is less than or equal to negative 5, k of x equals x if it's between negative 5 and 1, and it equals 7 minus x squared if x is greater than 1. They wrote 1 is less than x. It makes more sense to say x is greater than 1. So x equals negative 8 is going to fit with this part. So we'd write f of negative 8 equals 15. That's all you have to write. It's a constant, so you just write it down. Then for 5, we have to figure out, does it fit here? No. Does it fit here? Yes. So that's equal to 7 minus, now we put our 5 in for x, and now we simplify this. So that's the same as 5, or 7 minus, I'm going to change it to a decimal, 2.5. So that's the same as 4.5. So f of 5, let me just rewrite that, is 4.5, or 4.5, or you could even have it as a mixed number. And in proper fraction, I mean. All right, now we're going to look at graphing these. It's a little tricky to do in the online world because you have to use either Desmos or Sketchpad or the tools in Word or graph them by hand. So you do have a lot of options. So if you're going to graph this, both of these parts are linear. They're both a line. And you're going to have one of your lines is going to be for everything less than 0, x is less than 0, and the rest is going to be for everything greater than or equal to 0. So one way we can do this is plug in, we're going to like do slope-intercept method. So this is our slope, and this is our y-intercept. So b is our y-intercept, and that's 3. But I'm going to put an open circle there because that's when x is equal to 0, and I can't have x equals 0 for the first part. And then I want my slope to be 1/4. Normally I would go up 1 and over 4, but that would be the positive part when x is greater than 0, and I want the negative part. So I'm going to go down 1 into the left 4. 1, 2, 3, 4. And I'm going to put another point. And then I'm just going to connect those points to draw my first part of my function. Now for the second part of the function, it has a y-intercept of 3. Oh, so did the other one. So I have to put a closed circle there. They kind of overlap each other. And now the slope is negative 2, which means go down 2 and over 1. Down 2 over 1. So then I would go connect these lines. Something like that. Their lines are straighter than mine. Okay, this one's easier. This is a step function, so these are constants. So f of x equals 4, which is the line y equals 4, which is a horizontal line going through the y-axis at 4, for x is less than or equal to negative 1, and y is equal to negative 2 if x is greater than negative 1. So for the first part, you just put your solid dot because it's less than or equal to negative 1, and then we just have our straight line going through, it would go through y equals 4, but we don't want it to go that far, so just a straight line right there. And then for the other part, it's negative 2 for x is greater than negative 1. So we'd use an open circle because we do not want to include the negative 1 there. Here's another one to try. This again is going to have two lines. And part of it will go from up to 2, and the other part will go from 2 and greater than. So the line y equals negative 3x has a y-intercept of 0. And then the slope is -3 over 1. So I go down 3. Oh, but these are going every 2 units. That always messes me up. So down 2 and down another, there's down 3, and then over 1. And I'm also going to go up 3 and to the left 1 so that I have more points to draw this to. Now I'm going to start here. I need a ruler. It's only going to go to 2, and it's not going to include 2, so there'd be a hole there, an open circle, and it would go that way. Okay, and then the other part has a y-intercept of 3, so that's about right here. But I'm going to use it to make my line, but I'm not going to, I'll erase it when I'm done. Okay, so then it has a slope of 1 over 1. So it'll go up 1 over 1, up 1 over 1. There's where I'm going to start, is right here. Up 1 over 1, up 1 over 1. So I don't need this part of it. I'm going to start right here, put a solid dot, and go like that. Oh, mine's pretty bad. See, they didn't go, no, mine's better. They went down 1, 2, 3 squares, but that was down 6. So there's had an error there. And this part would not be included because I just used that to help me graph my line. And their line is bad, but I can't erase it now. Okay, note that piecewise functions are not necessarily continuous. They're usually not continuous. We had one so far that didn't have a gap, but many of them will have gaps. Okay, so to write the rules, that can be sometimes difficult. We use this formula for a lot of the problems. That ratio or distance equals rate times time can also be written as rate equals distance over time. That's just a note. But to write the functions, it helps to do more than one method. So use a table, use a graph, and then write your function. In this situation, we have Jennifer completing a 15.5-mile triathlon. She swims 0.5 miles, so that's right here, and in 30 minutes. So her distance is 0.5 miles, and her rate would be 0.5 miles an hour. Or no, it'd be 0.5 miles in 30 minutes, which is over time. So if it's a distance of 1 mile and she does that in 30 minutes or 1/2 of an hour, that's the same as a, there. She can go 1/2 mile in 30 minutes, which is 1/2 hour. So if we simplify this, 1/2 divided by 1/2 is 1 mile per hour. That's what this one came from. Okay, she bicycles 12 miles in 1 hour. So her time for biking is 1 hour, and she went 12 miles. So her rate is 12 miles per hour. And her running rate is 3 miles in 30 minutes. So if she can go a distance of 3 miles in a 1/2 hour, if we simplify this, that's the same as 6 miles in 1 hour. Okay, so that's how we got those rates. We can use this to help us write our equations. First, let's pick our domains. So she swims for 1/2 hour. So her time for our domain for time is between 0 and 0.5. Then she bikes. And she bikes from 0.5 from the first 1/2 hour to 1.5 because it's for 1 hour. And then after that she runs for another 1/2 hour, so 1.5 to 2. Okay, so now we're going to graph this function. She started out, of course, at 0, and she went over to 0.5 hours is how this was the swimming section. And then this is 2, 6. So this is a half, or this is 1, and this is a half, which is how far she went after swimming. Okay, then she got on her bike. And of course she went faster. She went all the way for the next hour, and she got all the way to 12.5 miles because she had gone half of a mile by swimming, and then she went 12 more miles on her bike, so that's 12 plus 1/2 is 12.5. Okay, then finally she started running, and she ran for the next half hour, and she went 3 miles. So we have to take the 12.5 and add 3 to that, which gets us to 15.5. So I would start by putting the points on there and then connecting them. Now from this, we can determine the slopes of the lines, and we can find the equations of each section of that as well. So using the graph is really a very good way to find the function, the piecewise function here. All right, so the first part from 0 to 0.5, when t is between 0 and 0.5, this equation right here is the simplest one to find because the y-intercept is just 0. So that one is just going to be that we would take the distance is equal to the time. The slope is 1/1, and the y-intercept is 0. So that one's the easiest one to do. Okay, then the biking one is going to be found by taking the equation of this line right here, this piece from here to here. And that equation is found by, we're going to use the point slope form. So here's a point that is exactly on the line, and we know the slope is 12 because she went 1, this is a distance of 1, and she went up 12. So 12/1 is the slope, so we put that here. And for the y1 we use 0.5, and for x1 we use 0.5. So then we would have that y minus 0.5 is equal to, now I'm going to multiply that through. That's the same as 12/1 is the same as 12, so we have 12x minus 12 times 0.5, which would be 6. And then all we have to do is add the 0.5 to both sides, and we get y equals 12x minus 6 plus 0.5 would be minus 5.5. Okay, and then finally we do the same thing for the running. And when she's running, we had a slope of 6 because she went, it was really 3 miles in a half an hour, which is the same as 6/1. And then we can use this point, and we can plug that into the equation. Y minus 12.5 equals 6 times x minus 1.5. And we simplify just like we just did. So we'd have 6x minus 1.5 times 6. I think that's 9, but let me just double check here. 6 times 1.5 is 9. And then we would add the 12.5 to both sides. So y equals 6x plus 3.5. And that's how they got the third part. And then you just put all of this together using your domains and your function rules, and that's what you would have. Now that was a lot of work. You don't always have to do that much work because sometimes the problem will say, write the function rule for any one given part of the trip or the situation. And if you only have to do it for any one part, then it's simpler. For example, and I'll come back to number 11, but in number 12, this is from your worksheet, it says a car is driven 40 miles for 3 hours, 55 miles per hour for the next 2 hours, and 50 miles per hour for the 2 hours after that. Write a piecewise function that best describes or best represents the distance the car traveled for any one part of the trip. So that's the key to it being an easier problem. You can just figure out the rule for each part of the trip instead of the total distance at any given time. So the first one is 40 miles per hour, distance equals rate times time, and then you just need to figure in what is the time for that one when it's up to this much. And then the next one is 55 miles per hour, and then figure out what the domain should be. And then the last one is also going to be that. And then I did graph that function, and now the trickier one for number 13 is to do what we just did for that other example. Find the equation for each of these parts, and then that will be your piecewise function for the whole trip then. Now the first one is always the easiest one because the y-intercept is 0. We're starting at 0. And the slope is a rise of 120 and a run of 3. Or you can use this for your slope. So the first one is going to be the same thing that you got for if at any given time part. And then you have to include your domain here as well. And that was what, 3 hours? And then the second part is the little bit trickier one. Now we have to figure out the equation of this line. But we have 2 points given to us that are on that line. We can just pick either one of them. And then we can use the slope-intercept form in order to find the equation. Now the slope for this one is a rise from 230 to 120. So the rise is 230 minus 120, which is 110. And the run is from 3 to 5, which is just 2. So that's 55. Now that matches this. So we can use that for our slope. So y minus y1, I use the 230 and the 5 point, equals the slope is 55 times x minus 5. And then you simplify this and put that in for the second part. And then again, you have to, every time you have to do the domain. That's for the next 2 hours. Whoops. I haven't went back so far. Here's everything that we've done for the last 8 minutes. Okay. And I was going to write a 5 here. And then you do the same thing for the last section of the line. Use the points that are on there. And then I said we'd look at number 11. This one is a parking thing, figuring out the cost for 10 days. There's only 2 parts to this one. It's $20 a day for the first week, and after that the cost decreases to $17 per day. So graph this and see if you can do what we just did, writing the piecewise function with the more complex method for any given point on your trip. Or you can write it with the simpler one and just say this is for any given point on the trip. All right, let me know if you have any questions. Thank you very much.